Log on, tune in, find out. Another good idea from Cambridge.
So I'm very glad that we're having this day. I'm part of this program that's running here at the Newton Institute for 6 months, really concentrating on design and analysis of experiments. And this day is actually giving us a chance for some of us to get together and hear about actually what's happening amongst statisticians who are always based in Cambridge. Before I get going, is there anyone here who would count themselves as an ecologist? I just want to see how rude I can be. So,
raise my little finger.
Okay, right. So this is work that began out of the sort of clinic that we heard described this morning. I like to advertise that on Wednesday afternoons people can just come and knock on my door, and sometimes I can give them immediate help, and sometimes I just say, no, that's much too hard for me, and sometimes good collaborations develop. And this is what happened in this case. So afterwards I went away and I read some stuff in the literature, and biodiversity meant to be good. You've all read that in the newspapers. So what happens? Biologists get together some collections of species, and if you read what they do, quite often these are just random collections of species. So you put together, so your treatment, what I would call the treatment, is a set of species, but the way you put them together might have been random. And you measure something which is good for the ecology. And the general conclusion always seems to be, the greater the number of different species, the better the outcome. So this is why we've all got to care about not letting species go extinct. Well, so then we had a new postdoc at Queen Mary, and she wanted to be a bit more careful about this, and so she said she was going to do this more carefully controlled experiment. She's looking at 6 organisms. Because I'm not a biologist and I can never get the Latin names right, I'm just going to call them shrimps. But these are small things that live in fresh water and eat stuff. What do they eat? Leaf litter. So we've got these 6 types of shrimp. And so what she was intending to do, she would put 12 shrimps in a jar which had stream water and this leaf litter, and 28 days later come back and measure how much they'd eaten. So which 12 shrimp should she put in a jar? She had these 6 types, and so she had 6 treatments that I would call a monoculture. So monoculture A means all 12 shrimps of the same type A. Then she put them together in pairs, which I call duocultures, so that's 6 of one and 6 of another. And she went a bit further and said, well, we can have them in 3s. So ABC means 4 each of A, B, and C. And she was calling these levels of what she called richness, 1, 2, and 3. And of course, what she was expecting to find, that as richness increased, then that would have an effect on the amount of litter eaten. Well, you can do the sums, and you can see 6 monocultures, 15 pairs, 20 tricultures, making 41 altogether. The jars were experimental units. She knew about blocking, and she did 4 blocks with 41 jars each. Now, I had the word design in the title. When I found out it was only 10 minutes, I'm not going to say much about the design, but you can imagine we managed to do all 41 combinations there. If she started off with 8 rather than 7, you might not want to do all the possible combinations, and there are design issues. So she fitted her model with its 3 parameters, saying it should just matter how many species there are, and oh dear, she couldn't find any evidence at all that the number of species made any difference. So she came to me, and I said, show me your data. I actually want to see the data, not these horrible little summaries. And I looked at the data, and it seemed to me that something was staring me in the face. There should be a parameter for each monoculture. When you mix them half and half, you get about the average of the 2. And when you mix them in 3, you get about the average of the 3. So what's going on there? What you could say it is this way. If we've got xi shrimps of type I, then there should be a constant ai, which is actually a constant times that, such that the expected response is simply that sum. So in other words, shrimps of a certain type eat a certain amount of leaf litter in 28 days. You don't need to put an intercept in because we always had 12 shrimps. Thank you. So, her model had 3 parameters. My model had 6. Of course, they both have the constant as a special case. When I think about models, I always insist that if you've got one model and you've got another one, you should have their sum. What will the sum be in this case? It simply means that depending on whether you've got 1, 2 or 3 species, you add something to every level. Once you've thought about that, you can actually think of something that you might think of as an interaction, and that means that the amount that each type of shrimp eats can change with the level of richness, but it still is blind to what other species are there. Or right up the top, with 41 parameters, there's simply one outcome for each treatment. Well, the first interesting thing I found was I always draw diagrams of models like this, and the ecologists absolutely love them. Ecologists don't like looking at mathematics, they don't like looking at equations and symbols, they loved that. Not only that, they insisted that the ecology journal where we did the first work actually published it. Now normally it really annoys me if you're working with a biologist, the paper is 2/3 literature review and waffle. What you actually did and the data and so on and so forth is put on the web or in some supplement. And so the editor said, put this horrible diagram in the supplement, and the ecologist said, no, that has to go in the main paper. And then we wrote, well I wrote this, I said when we're looking at the ANOVA table, each row of the ANOVA table is for a difference between models. Does this model explain more than that? First referee said, you better go and talk to a statistician and find out what you're talking about. Well, we managed to persuade them that we did know what we were talking about, and we got away with that. And so we've actually done more experiments since on this line. And so this is what I'm going to finish with, showing you the results. So that was my Hasse diagram of models. And it occurred to me, if that's helping them to understand the models, perhaps we could display the ANOVA table in the same way. So what you're going to see now, it's the same Hasse diagram, but now the lengths of the sides have changed. They've changed to show the mean squares for that line of the ANOVA table. So that big bit there is the mean square for the middle model type. That tiddly bit there is the extra if you add richness on top of that, and so on. And there's a scale. I put 3 times the residual mean square so that you could actually see it. Well, we didn't actually, I only thought of this later, so that's not been published. But the conclusions which any old fool should be able to read off that diagram is that the model richness does not explain the data. The model type accounts for almost all of it, explains the data well. And there really is no evidence that any larger model will do any better. If there'd been a lot up there, we could have gone on to fit some more complicated models above that. So we actually, thank you. After that one experiment, we did another, and I was involved in the design. There were 2 responses measured on each. So altogether, we've got 4 ANOVA tables, and they're all very similar in their conclusions, that really each type of shrimp eats a certain amount of stuff, and biodiversity is neither here nor there. But so I thought that was interesting, a way of working with a class of biologists I hadn't worked with before, and the fact that the model diagram really seems to work for them, and then this suggestion that you can express the ANOVA in that pictorial way. Thank you.
Any question? I really like the ANOVA representation, but the question on the ecology, I guess, would be, I thought one of the arguments for biodiversity is meant to be robustness to disease. That seems to be a typical one. So if I have a monoculture, then I get some disease and it will wipe out.
It will get wiped out, yeah. Yes. I mean, I think it's quite clear here they were just measuring one rather small thing. And if you went up to a system where that sort of thing could happen, you might get different outcomes. Yeah, I agree.
Very quick, did you get your ANOVA diagram published as well?
I haven't tried to get that published yet because I only thought of it after the 2 papers were in press. But if I'm getting generally positive responses, so I'm going to try and get that published later this year. Yeah. So any suggestions gratefully received.
To the next speaker, last time, Rosemary again.